Okay, in this little lecture video, we're going to start talking about Chapter 2 in Leninger, which is all about the biological solvent water. So a lot of this is going to be review, because it's just going to talk about basic chemistry of water molecules. So first of all, what we know about water is that it's a really unique molecule. It has a high melting point, a high boiling point, a high specific heat, a high surface tension. It has all of these interesting, unique properties. So the question is, why? What is it about water that makes it so special? And the answer to that question is that it is the cohesive forces amongst those water molecules. How do you spell amongst? Amongst the molecules. So if you think back for a minute to those 5 types of intermolecular forces that we've discussed, and you look at the structure of a water molecule, which looks something like this, you hopefully look at this and come up with the fact that the intermolecular forces most likely to take place between water molecules are going to be hydrogen bonds. So we know that water has a Lewis structure that is bent. We know that oxygen is more electronegative than water, so you get dipoles going from the hydrogen to the oxygen with more electron density around the oxygen atoms. So we get a little bit of slight negative charge up here and slight positive charge down here by the hydrogens. And when we look at this, we can see then that each water molecule can form up to 4 hydrogen bonds. It's got 2 hydrogen bond donors, one each hydrogen, and the 2 lone pairs of electrons on the oxygen atoms can serve as hydrogen bond acceptors. Now these hydrogen bonds that form between water molecules break and reform quite rapidly because the hydrogen bond is relatively weak. So a hydrogen bond between water molecules, which we would represent like this with this dashed line because it's not a sharing of electrons, so we don't show it as a solid line. So a hydrogen bond is about 20 kilojoules per mole. If we compared that to a covalent bond between an oxygen and a hydrogen, like in a hydroxyl group where you have sharing of electrons between an oxygen and a hydrogen, that bond strength is about 470 kilojoules per mole, so a lot stronger. Now that 20 kilojoules per mole is so low that it can be broken at room temperature. So there's enough energy at room temperature to break those bonds. So again, those hydrogen bonds break and reform rapidly. However, since each water molecule can form up to 4 hydrogen bonds, even though they're breaking and reforming rapidly, they're additive. So overall, those hydrogen bonds are a big contributor to the cohesiveness of water molecules. So because we have this network then of hydrogen bonds between water molecules, whenever you add something to water, you disrupt that hydrogen bonding network. So those hydrogen bonds have got to reform. But hydrogen bonds can be reformed with other groups as long as those other groups possess an acceptor, A, whatever that atom is, and a donor, D. We'll also represent the donor by D. So in this notation, you've got a donor atom, which is attached to the hydrogen that's going to participate in the hydrogen bond. So we know that that donor has got to be more electronegative. That's a delta minus than the hydrogen. And then that hydrogen can form a hydrogen bond with whatever that accepting atom is. So common ones, for example, would be oxygen, nitrogen, sulfur. So, for example, in the case of ionic species, those are charged. So they go easily into water because they can form hydrogen bonds with the water molecules themselves. So they become easily solvated, or since we're talking about water, easily hydrated. The same is true for other polar species. So if you look at figure 2.6 in your book, on page 51, you can see that where you have hydration of sodium chloride. But the next question is, what about nonpolar solutes that are incapable of substituting into that hydrogen bonding network? They don't possess any donor or acceptor atoms that could form hydrogen bonds with the water molecules. What do they do? So we know that if you take a nonpolar moiety, like a hydrocarbon, oil, and you put it in water, that it doesn't mix. So oil plus water does not mix. We know that. Everyone's made spaghetti. So the question is, what is it? What's happening to that hydrogen bonding network in the water molecules, and why are things not mixing? Well, it turns out that the whole process of why things mix together, and it's going to come in a lot when we start talking about the structure of biomolecules, is because of entropy. So when you take a hydrophobic solute, and I'm going to represent hydrophobic like this, so that means does not like water. When you put a hydrophobic solute like oil into water, you not only disrupt water's hydrogen bonding, but you also disrupt the entropy of water. So if you've got a beaker full of water molecules, here's my beaker, and it's full of water molecules, they're moving around all the time forming their hydrogen bonds. So the hydrogen bonds form and they break. They form and they break. And the hydrogen or the water molecules themselves are always switching partners. Okay? But if you put a nonpolar solute into that beaker of water, so I'll just represent that by a big circle of nonpolarness. So when you put that nonpolar solute into this beaker of water, and I'm going to represent my water molecules by these arrows, so that's equivalent. Now you've got this case where you've got these water molecules that can no longer switch partners. So what they end up doing is they reform something around that nonpolar solute called a clathrate cage. Okay, so here's a picture from an old edition of Voit and Voit, which is a biochemistry textbook, and I can't find this picture anymore. It's not in the new book, but all I have it on is this transparency, which is totally unfortunate, but here it is. So this is the clathrate cage. So what you can see here is the nonpolar solute in kind of this orange, and you see these water molecules that have essentially formed this barrier around it so they can form the best hydrogen bonds that they can. So that all the nonpolar groups are clustering together. So for example, when you put oil in your spaghetti water, the oil all stays together because these water molecules are forming this shell around them. And that allows them to maximize their hydrogen bonding capability, but at the same time, it also decreases their entropy. So we know that when you have a hydrophobic moiety, some nonpolar solute in water, that it doesn't dissolve because it's entropically not favorable. Not because the entropy of the nonpolar solute, but because the entropy of the water molecules. And water is 55 molar. It's highly concentrated. There's a lot of water molecules in a sample of water. So when you're talking about changing the entropy of the water molecules, that's a big contribution to the overall free energy of the universe. So when you're talking about likes dissolving likes, what matters is the entropy of the water molecules and how it's affected. So if we look then, if you go back and remember, just in terms of entropy, when we're talking about the second law of thermodynamics, and we're talking about delta S of the universe, we know that that's composed of delta S of the system plus delta S of the surroundings. And we're so used to thinking about entropy changes of our system. But the third law, or the second law of thermodynamics, what really matters when you're talking about water is the delta S of the surroundings. So we'll be talking in this class about how these properties of water play a role in biochemistry, particularly how they drive the formation of protein and membrane structure. So the first contribution will be considering the entropy of water, and then in other videos we're going to talk about the other characteristics of water.